All right, so what I'll do is go over the exam problems. So hopefully you can get clear about how to do these problems for those who didn't understand how to do all of these problems. And these problems will appear on they will reappear on the final exam. So it's good to keep practicing. And if you didn't get it this time around, then you have another chance on the final exam to get this right, okay? So let's look at the first one. Count occurrences. So this is a function, and it takes an array of int and an int that represents the length of the array or the number of elements in the array, and a third argument, which is another integer, which is an item to look up inside the array. If you're arriving late and you want your exam, you can search for it through these papers here. Want your exam, it's right there. So, the problem is to find the position. Oh, sorry, no. The problem is to find how many times does K occur in A. Here's the function. How many times does K occur in A? Now, in the exam, you didn't need to copy this again, but if you did, it's okay. So what we need to do is look at every item in A and say, for each item 0, are you K? No. Item 1, are you K? Item 2, are you K? Each time we get a yes response, we increment a counter. That's how we keep track of how many times K appears in A. So we'll need a counter, and we'll initialize it to 0. And then we need to look at every item. That means we have to examine the value in the array at every possible index. So we need a variable that ranges across the indices. So the typical variable to use is I. It stands for index. It also stands for integer, the letter I. And we don't want I to hit length, because that's the end. That's one past the end of the array. And when I starts at 0 and I goes to n minus 1, position n minus 1 is valid, but position n is not a valid position. Once again, that's because counting starts at 0. So we check for each index I that's ranging across all the valid indices for A. For each index I, we want to check what's at A of I. Is K, does A of I, is the value at I, does it equal K? If it does, we increment the counter. Now finally, after we've done looping and we've incremented the counter, then we return the counter. So that's how to do that one. What about the next one? When the code in figure 2 runs, what does it print? Well, let's take a look at it and analyze this. Here's the code. And if you look at it, you'll see there's two variables. There's n and k. And in the first line, So we execute this line by line. That's the first line, the first statement. This is the second, third, and fourth statement. So there's 4 statements. Once again, the problem is asking, what does this print? What does it print? So we see that there's this output operation in the last statement. And we have an expression to evaluate here. And the value of this expression is passed to the output stream. It's passed to the output operator, which operates on the output stream. So let's go line by line. This is the first line or first statement. It declares a variable n and initializes it to 5. Now in the next statement, we declare a variable k and we initialize it to something. And that something that we initialize it to is the result of this expression. And this expression has 2 operators. It has the pre-decrement and multiplication. A pre-decrement is done first. And this pre-decrement is done immediately. We don't wait for that. So it's different. The post-decrement is evaluated after we read the value from n. Here, we modify the value of n and then read and use the value of n. So if we modify n, n becomes 4. So now this sub-expression has evaluated to 4 and has had the side effect of changing the value of n. That is a side effect. So 4 times 2 is 8. So this expression is now 8. 8 is assigned to k. So we're done statement in line 3. What about the statement in line 4? So here we're going to add to k the value that's the right-hand side of that operation there. So we need to evaluate this expression and assign it or add it into k. So this is a post increment. That means we use n first and then we increment later. So if we use n, n is 4. So 4 is added into k. That means k becomes 12. I keep it like this. The k now becomes 12. And n started at 5, by the way, and went to 4. So k is at 12. So we've just increased k by 4 by the value of n. And now we need to decrement n. So n becomes 3. And we're finished with the statement in line 4. Now the statement in line 5 is an output operation. We evaluate the right-hand side and send that to the output operator, which operates on the output stream. So here we multiply n by 3 and then add k. That becomes the value of that expression. So n times 3 is 9, plus k, it's 9 plus 12, so that's 21. So we print 21. Any questions on that one? Okay. What about number 3? Implement the function sum whose declaration appears in figure 3. The argument of the function is a 100 by 200 two-dimensional array of double precision floating point values or numbers. The function returns the sum of all the values in A. So when it look at every value in A and add it to some kind of an accumulator. This is similar to count occurrences. It's essentially the same logic as count occurrences. We look at every value in the array, increment this counter. We're counting occurrences. Here we're summing. So we want to start with some kind of an initial value set to 0, a variable set to 0, and examine each item and add that into this to this variable. So let's take a look at this one. So we need to range across. Well, let's declare our variable. We'll call it total. Set it to 0. So we'll keep track of the total as we look at each item in A. We'll increase total by the value that we find. So we'll need a loop. So we'll start with the rows. I'll use R for that purpose. There's 100 rows. And for each row index, for each row, we need to scan across all of the columns in the row. That's when we look at each item. So we need another loop. We need a loop within a loop. So we have a column index. So now we have a pair RC, a row column index pair. And that lets us examine the value at ARC. So that's the value at ARC. And we're going to look at every possible value here because we're looking at every row. And for each row that we look at every column in that row. That's how we do it. We have a nested loop. So take the total and add into the total the value we find at RC. And when we're done looping, we simply return the total. How about number 4? When the code in figure 4 runs, what does it print? So we have to analyze this code. And I'll take a look at it over here. So you'll see that it's in line 5 here, this statement that prints something. That's the only place that we print. So we're not printing inside the loop, right? If we were inside the loop, this would probably be indented, see, inside of the while loop. It's not. We're outside the loop. Last thing we do is we print I. So we just have to figure out what I equals after the loop finishes. The first statement is this one. The second statement is that. It's a compound statement, a while statement. It has a substatement in it. The second statement is a loop, and the third statement is that output operation. We only have one variable to keep track of, I. And we start by initializing I to 66. And then we execute the while loop. So the first thing we do is evaluate the loop condition. The loop condition is true. 66 is bigger than 3. And so we replace I with I divided by 2. So I divided by 2 is 33. I becomes 33. And then we're at the bottom of the loop, so we check the loop condition. The loop condition is still true. So we replace I by I divided by 2. So 33 divided by 2 is 16. That's integer division. It's not 16 and a half, it's just 16. Everyone get that? And now we check the loop condition. 16 is greater than 3. So we divide I by 2 again. As you can see, we're just dividing by 2. We just keep dividing by 2. And when I becomes 4, the loop condition is still true. So we divide I by 2, and then I becomes 2. And now the loop condition is false. That means we terminate the loop. But I is left being equal to 2, so we print 2. Any questions on this one?
Wait, so how'd you get 16? Because I thought like you can't use decimal.
What's that? How do you get 16? Well, when I is 33, okay, that means the expression we have here is 33 divided by 2. That's integer division. Those are both integers. What's 33 divided by 2 as an integer? It's 6, but as a floating point value, it's 16 and a half, right? But you can't put a half in an integer variable, so we drop the half part. We just get 16. All right. My maximum. Provide an implementation of the my maximum function, whose declaration is shown in Figure 5. The first argument of the function is an array of int, and the second argument is the number of ints that are in the array. The function returns the largest number that is in the array. So, you know, like all the other array problems, we have to scan across the array looking for the biggest value. We need to find the biggest value. So we're going to end up scanning across the array. So we need an index for that. So the size of the array is n. That's passed in as the second argument. Because arrays don't have their size embedded in them as a piece of information, unlike vectors. So we have to pass that information around separately from the variable a itself. So let's look at every possible index that's valid for a. And then we're going to say, well, if we look at a of I, we want to know if it's a new biggest value. So we need to compare it to some record of the biggest value we've seen so far. And we'll just call it, I'll call it biggest. So we need to have something that keeps track of the biggest value we've seen so far. So we use this variable biggest. And we set it to AI. When we find a new biggest, then we reset biggest. We set biggest to that thing that we find. So whenever we find a value that's bigger than biggest, then biggest becomes the new high value. But we have to start somewhere. Where do we start? Well, we don't want to start at 0. Because what if the array has only negative values in it? Then 0 would end up being the biggest value, but 0 is not in the array, and 0 is bigger than everything in array. So we can't start at 0. So what we do is we just take the first value in a. We need to take some value in a. We don't know how small the biggest value is. We cannot assume that it's bigger than 0. We don't care what it is, but we'll just use a of 0 as a starting point. And then at the end of the loop, we just return biggest. Here we go. That's how to do that one. Any questions on that? These are all very similar, aren't they? They have these loops in them. And you examine every value. These are linear algorithms. We just go, one after another and make some operation. So that's the template that we're using to solve all of these problems. It varies a little bit. Like for the two-dimensional array, we need to loop within a loop because each row is treated as its own sort of one-dimensional array. So for each row, we want to scan across all of the columns. So it's a loop. It's a nested loop. But try to get used to this template, this basic idea. We look at one thing after another. Not all algorithms do that. Like binary search does not do this. Binary search is not a linear algorithm, but most of the problems in this class, all other problems in this class, other than sorting, are linear algorithms. All right, let's look at the next one. Write code that prompts the user to enter a number between 3 and 12. If the user enters a number inside 312, the program displays good number, otherwise bad number. So 3 to 12. So there's the prompt. Enter a number between 3 and 12. Let's read it in. So that's the first step, to get the user input. Now we want to check to see that it's between 3 and 12. So if the value read in is greater than or equal to 3, and I'll write and this way, because that's how you usually see it, even though A and D is valid these days. And n is less than or equal to 12. If that's true, then we print good number. Else we print bad number. There it is. Any questions on that one? Write code that prints 4,000 random numbers in the interval 100 to 200, where 100 is included in the interval, but 200 is excluded. 4,000 random numbers. So we have to do something 4,000 times. So we need a loop that runs 4,000 times. That loop runs 4,000 times. Now inside this loop, we want to print one random number. Then we'll end up printing 4,000 random numbers. So let's calculate a random number. I'll call it R. So that's a random integer right there. Well, we want the random number to be between 100 and 200. So basically, the smallest value that we want is 100. And so we want to go from 100, we want to go at most 99 more to get to 199, because 199 is in this interval, but 200 is not in the interval. Because the way we wrote it here, we're excluding 200, but we're including 100. That's what I said, right? Let me check that. So we start at 100 and we add from 0 to 99. So start at 100 and add from 0 to 99. That's it right there. Oh, I'm sorry, that's not correct. I got that wrong, didn't I? It should be 100. That's a little tricky, isn't it? So that's how to generate a random value in an interval. You have to think about it a little bit, right? See, rand, the smallest value that rand returns is a 0. So the smallest value that that expression that I have highlighted, that smallest value that that expression takes on is 0. That means the smallest value that's assigned to R is 100. See, that's one way to check your reasoning. So that gives us the smallest value of 100. And then we want to go from that 100, we want to go up another 100 or 99. So we want a random value that doesn't exceed 99. So that gives it to us. If we mod 100, the largest value we'll get is 99. Suppose that n is an integer greater than 1. Write code that determines whether n is prime. The program should print prime when n is prime and not prime when n is not prime. So we have some value n. So it's a given, n exists. So what we'll do here is look at all the values starting at 2, strictly less than n, and see if we can find a divisor. If we find a divisor for n, if n mod I equals 0, it means we found a divisor. So there's a couple of ways that I would accept the solution. I'll show you a couple of ways. Here's one way that I accept the solution. Start with a Boolean variable called isPrime. Set it to true. When we find a divisor, then we change isPrime to false. It's not, so this variable represents our assumption that the value n is prime. Here we correct our assumption, because now we know it's not prime. And then if isPrime is true, then print prime. Else print not prime. You can do it like that, or you can use the brackets. So the other form is okay, this form is good too. Another way that I would accept this solution is to do this. Actually, no, I wouldn't do this, would I? Because you can't print it like this. This you can't print. So that's a simpler way to look at it, but you can't, there's no printing there. Oh yeah, we could do it like this. We could do, here we go. We could print prime, not prime here. Yeah, there we go. This will work. And then we return. And then here we print prime. I don't know if anybody did this, but I would take that. But I don't think anyone did that. The other solution, I think, is better. Because this assumes we're inside of a function that we want to return from. And it's okay if you made that assumption. Any questions about this one? Remember, this is pretty simple about prime numbers. You just scan across all the values. You look for a divisor. If you find a divisor, you know, oh, it's not prime. That's it. So that's the core of this algorithm. And I do want to say, although I don't want to confuse people, but it's a bit more efficient if you take the square root here of n. It's going to run a lot faster, but you know, you don't have to put that in there. Just to let you know, it's not very efficient the way it's written. Okay. Suppose your home directory contains a folder named temp. And in this folder, there is a file named a.out. Show the UNIX command to delete the file a.out in the temp folder. Make no assumptions about your current directory. So under temp, there's a file named a.out. Under temp, in the home directory, there's a temp, and in that temp directory, there's a file a.out. How do you delete it? You just delete it like this. So you give the path to the file. That becomes an argument of the rm command. It doesn't matter where we are in the file system. We're giving the full, it's not a relative path. It's called an absolute path. It doesn't matter where we are. If we did something like this, oh, that's called a relative path. So we're saying go up to our parent folder and then down into a sibling folder named parent temp and then find the file there. But we cannot make the assumption that our sibling folder is the temp folder with a.out in it. We can't make that assumption. So we have to use the absolute path to the file. So we start at the home folder, go into the temp folder, and find a.out inside there. All right, number 10. Show the UNIX command to list the contents of the parent folder of your current directory. In other words, the directory that contains your current directory. So list the contents of the parent. That's it right there. List the contents of the parent. ... represents your parent folder. We just use that as an argument to ls. You can do that if you like. That's also okay. But that's shorter. All right, number 11. Suppose you have a file named main.cpp in your current directory. Show the UNIX command to create a copy of this file named test.cpp. The copy should go into your current directory. So main to test. So copy main.cpp to test.cpp. There it is. Copy source to destination. Everything stays right inside of our current directory. We don't need to have any folders. We don't need anything like that in front of the file names. Everything is just immediately available to us. So this creates a copy of main.cpp and gives it the name test.cpp. But 12, show the UNIX command to move a file named main.cpp from your home directory to a folder named lab1. Assume the lab1 folder is in your home directory. Make no assumptions about your current directory. So we don't know where we are in the file system. That means we need to use absolute path names. So move main.cpp from our home directory into a folder named lab1 in our home directory. So move from our home directory a file named main.cpp. Move it into the lab1 folder that's in the home directory. There it is. If you like, you can do this as well. That's good to do, but you don't have to do that. So those are two absolute path names. They both start at the home directory. Doesn't matter where you are in the file system. Those paths will start in the home directory. If you omit this, if you do something like this, then it's relative to where you are in the file system, but we don't want to make no assumptions about that in this problem. Any questions on this one? Is unlucky. Implement a function that determines if the unlucky number 13 appears in an array. The function returns true if 13 appears in the array at least once. Otherwise, it returns false. Implement a function that determines if 13 appears in the array and it returns true. It must be unlucky. Otherwise, it returns false. So just like the other problems, we need to scan through the array. We have to look at every value in the array. In the worst case, it could be we find a 13 in the first slot, and then we don't have to look at everything. But in the worst case, we look at everything. So we have this template here, this for loop that scans across all of the valid indices of A. If we find a 13 at I, then we're going to return true. It's unlucky. When we complete the loop, we don't find anything. We can finish the loop. We have to look at all the other numbers. We can't have an else statement in there. If we have an else statement in there, then we'll terminate the loop when I is 0. We never get a chance to look at the other values. Maybe we'll find a 13 of position 1 instead of returning. We don't want to return false after just looking at A of 0. We have to look at A of 0, A of 1, A of 2, and all of them before we return false. False means we didn't find a 13, but that means we've got to look at every one. Okay, so it's outside the loop. Question? And that's it. Any comments about the exam or the course? You can anything that you want to bring up or talk about. I know the material is hard. Some students have suffered on this exam, I know. And you can still do okay in the class if you haven't done well in the first exam. If you didn't do well in the first exam, it's a wake-up call. You've got to make a shift in how you prepare for the exams of the future. You've got to practice. That's what I think. I think you need to put time into practicing the material. It's all about practice. And maybe that's not possible. A lot of students are very busy. They don't have time to practice. So, but that would be a barrier. I wouldn't know what to do with that barrier. I mean, that's just a barrier. But if you have time, you've got to practice. And these are not impossible problems. They push your knowledge and skill a bit, don't they? But they're not impossible. This is not impossible. These are pretty small, compact problems. But it takes practice. You've got to practice. If you don't put the time in to practice, and you got to practice the right way, of course. You can't just like read it or listen to my lecture over and over again. That's not going to do it. You need to create your own tests, your own examples, and play with the material to get skillful with it. All right. So what are we going to do now? We ran through that pretty fast. We talked about vectors, right? We did vectors.
It would be nice to explain it
Huh?
So it'd be nice to get like another explanation.
Go again on vectors, right? So here is this the one that's due this week?
Yes.
Yeah, okay. And about the old assignments, don't give up. Go back. If you didn't submit the old assignment, submit it late. I'm taking them late, okay? I don't know if you noticed that, but if you show me that you're working and you go, yeah, I spent time on this, send me the link to your workspace and say, hey, I redid or I did the problems from assignment 3. That I figured it out, and give me whatever points you can give me for that. I'll take a look at that. I'm happy to see you put the effort in, and it'll pay off for you. If you go back to the older assignments, if you didn't get the older assignments and you're just working on the new ones, you may not have sufficient understanding of what you're doing. So you got to go back and master the old assignments first. All right, so let's look at this. Which one of these do you want to look at? Look at all of these or any of them.
Number 2.
2, good, thank you. Appending integers. So here we have a function, it's called append. It takes a vector of integer v and an integer n, and it appends onto the vector the values 0 through n minus 1. Write test code to thoroughly test the function. So it's kind of an artificial problem, but I had to come up with something. Let's do this one. We don't need that. So here's the beginning of a program. We have to include the vector header, by the way. We'll need to use assert for the test code. And here's the function. And we'll just have it do nothing. That's our stub right there. It doesn't notice it returns void. So we don't have to return anything. So we'll leave it alone. If we like, we could have a return statement in there without returning anything. Just say return by itself. That works. But the compiler, when we get to the end of the function here, line 8, the compiler will just generate a return for us. So we don't actually need to include that return. Here's a vector, b, And let's push some of this stuff onto here. Just have a size 3 vector. So push back a -9, a -4, and a 0. So the vector will be -9, -4, and 0. It doesn't need to be in order. So just to prove that, I'll make this a +9. There we go. We don't need a increasing vector for this problem. So we just have some vector v, and then we're going to call the function append. We'll pass in, say, a 2 or a 3, so a 3. And we'll need some assertions here. So the vector looks like this before calling the function. Then after calling the function, we want the vector to look like this. Was it n-1?
Yeah.
So we're appending 0, 1, and 2. So, 0, 1, 2, all the way up to n-1. N is 3, so we stop at 2. It's a little confusing because there's already a 0 in there, right? But the instructions say to just append 0 through n-1. So we're going to end up with 2 zeros. That's okay. So now we want the test code to check for this. So we assert that v of 0 equals 9. And v of 1 is -4. And v of 2 is 0. V of 3 is also 0. V of 4 is 1. And v of 5 will be 2. So we got, and then all tests pass. So we have our test code written. See, one of the reasons to write the test code, in addition to having test code, is it helps you understand what the function is supposed to do, right? So we pass this value in, we pass that vector in, and the function modifies it to become this. All right, so I think we're clear about what we need to do. Now let's watch and see the test code fail. Since we could put another test in there, by the way, I'm going to put another test in there because I see a problem. The size should end up as 6. All right, so the size before calling the function is 3. We have 3 items in V before calling the function. After we call the function, we add 3 items. So now the size should become 6. So that's the test that will fail in line 18. So we're very deliberate about this, right? We know exactly where the test will fail. It will fail in line 18 because we didn't do the function yet. We didn't implement it. We only have a stub. So let's watch that. Line 18, right there. Assertion, the v dot size equals 6 failed. Okay, so exactly what we expected. Now, if we had left that out, by the way, then this assertion would pass, that would pass, that would pass. But what would happen here? 3 is not a valid index in the array because there's only 3 items in V. In other words, the valid indices are 0, 1, and 2. So what do we do when we do V of 3? Well, I tell you, it's unexpected. We don't know. In all other languages, practically, we'll get an exception and we'll say, index out of bounds error, something like that. So that index is too big. The runtime system will tell us specifically that your index is too large. But in C++, it won't do that. And that, by the way, that check for an index out of bounds, that takes some CPU resources to do that. So some programmers that are programming things that need to run quickly, and they're trying to shave off clock ticks here and there wherever they can, will work in C++ or C for that reason. All right, so I don't know. So this might actually, I think this might actually not fail. But maybe line 23 will fail. That's my guess. And we'll just check it out. But it's not a good test. I was right, 23. Because I was guessing that there would be, that's some place in memory that we didn't initialize. So I was guessing that, maybe it was a 0. And I was lucky, it's a 0. But in the very next part of memory, it probably found another 0, and it didn't. And it didn't equal to 1, so that's where we failed. But this is a bad test because we're depending on something that's unpredictable. Although I did predict it. But this is a better test because we keep in control here. We know why we're failing. We're failing because the size of the vector is not the right size. All right, so let's implement the function. So we'll need a loop because we don't know how big n is. So pushback is the function to add a value to the end of an array. So we just let I range from 0 to n minus 1, and then push each of those values onto the back of V. That's it. And the test code should succeed now, and it does. So look at all the work was done with the test code, wasn't it? When we finally got around to implementing the function, all we had to do is put that little bit in there. And most of our time is spent reasoning and checking, getting the program to compile, preparing the test code. Any questions on this one? Yeah.
Can you explain what the parameters do and mean?
Oh, yeah, thank you. Thank you very much. I want to show you this one here. This is a great question, and I should have remembered to do it myself. Thank you for remembering for me. Let's suppose we take that ampersand. You see the ampersand here, everybody? Let's take it out. Is that going to compile? Yeah, that'll compile. No problem. What about the test code? What's the test code going to do? It'll fail, okay? Because we're making a copy of the vector that's coming in. And then we're pushing back onto the copy. So the vector that's here, this vector here that we created right there, that vector remains unchanged. See, that ampersand means reference. It means I want a reference to the vector you passed into me. If you take the ampersand out, I don't want a reference anymore. I want a copy. And now I'm operating on a copy. So the original vector that was passed in, that remains unchanged because we changed the copy. So given that understanding, where's the test code going to fail? What line? Which line do we get an assertion failure?
Would it be 21 or no?
21? Anybody else? 21. That sounds good. Because, I mean, if he doesn't change, well, that's okay. We didn't even call the function yet. Well, the size will still be 3. (21) size equals 6. You see, we didn't modify v. We didn't add any numbers onto v. We added values onto the copy of v that we made here. We don't want that. We want to add numbers onto the vector that's in the calling code. So we want a reference to the vector in the calling code. So we tell the compiler with this ampersand, give us the original vector, don't make a copy. Everybody got that? All right. And this is not just C++. This concept of reference versus copy is an issue in all languages. You have to be always aware of this. In any language that you're working in, this is a major issue. Are we out of time? Not yet. So I'll set that back in there. Is that enough, or do you want to do another one? Enough? Four? How many people want to see 4? 1, 2, 3, 4. Okay, I'm going to do it fast, okay? I won't do a lot of explanation. A vector insertion. Suppose a vector v contains a sequence of integers ordered from lowest to highest. For example, v might contain 3, 6, 7, and 12. 3, 6, 7, and 12. You know, we don't even have to read any more to make the test code. 3, 6, 7, and 12. 3, 6, 7, and 12. So this should be, 3, 6, 7, and 12. I'll do it like this. So right in the problem statement, we've got a nice test case to use. We have a vector whose values are in increasing order. There's 4 in there, right? Write a function called insert that takes this vector v as a first argument and an integer k as the second argument. We can just digest that information right here. And here's our function insert. We don't even have to read the whole problem. And that's a k, right? And I'm going to leave that loop in there because I'm probably going to need it. So we're going to call insert here. And the result will be something. Write a function called insert that takes this vector v as a first argument, integer k as a second argument. The function inserts k into the vector so that it preserves the order of the elements. For example, if we have 3, 6, 7, and 12, which we have in our test code, and k were 5, then after the insert we will get this. Oh, look, the vector class has an insert function, but we're not allowed to use it, okay? Because we're trying to learn how to do linear algorithms. So 5 is the test case here. So we want to put this, the vector should come out like this if we insert a 5. So it has to come after 3 and before 6. So the size of the vector afterwards should be 5. 5 elements after the function runs. V0 should be 3. V1 should be 5. V2 should be 6, 7, and 12. Then all tests pass. There we have the test code. Let's run the test code and watch it fail. That's because we don't do anything. Now, how are we going to do this? Oh, this is a bit tricky. And I'm just going to show you the solution quickly, and you can think about it. We got to make the vector 1 larger. So we're going to push k onto the end of the vector to make it 1 bigger, but k is in the last slot. So we're going to swap it with the previous element until it gets into the right position. So we'll have a loop there. We're going to compare v of I if v of I is less than v of I plus 1. There's a couple of ways of doing this. So it's hard to do this quickly. If I will point to where k is, I'm going to have I point to where k is, and I want to compare where k is with the value just before. I'm sorry, no. I plus 1 will be where k is. Maybe that's too confusing. I is where k is. I minus 1 is the one before k. The thing before k is less than k, or say equal to k, then we're done. Then k is in the right position. Otherwise, we have to swap these. Yeah, this is the hard problem, isn't it? So that means we start with the last index, which is v dot size minus 1. That's the last index. And then the loop condition is going to be that I is greater than 0. That means the smallest I can get is 1. So we'll compare, k. That means k would get to position 1. We're going to compare k, which is in position 1, with the value in position 0. If it's greater than the value in position 0, we return. Otherwise, we swap. And if we swap, in that last case scenario, k is now in position 0. And then we don't need to do anything more because k has been put into the first slot. So our test code needs to be expanded. I'm going fast, right? So we don't really have time for this. Not too bad, 5 minutes to go. The test code is inadequate. This is okay, but we'll need another test. We got to try inserting a value that's smaller than everything else, like 1. I'm sorry, that's not right. This is 6. Well, we're going to insert a 1. So that means 1 will go all the way to the front. See, this is called the edge case. We should also test the case where we don't do any swapping at all. We just append it onto the end. That's the other edge case. There's 2 edges here. So we check the edge case. So now V of, it'll look like this. V of 5 is 12. V of 4 is now 7. V of 3 is 6. V of 2 is 5. V of 1 is 3. V of 0 is 1. Is that agreed? That's what the vector should look like after we insert this 1. So that's the edge case where it gets all the way to the front. I think I got it. It failed. Line 26, right here. Oh, we pushed 3, 6, 7, and 12. 3, 6, 7, and 12. 3. Oh, so it didn't work. Did not work. So 3 was in position 0, but 5 did not go to position 1.
So that's what,
Yeah.
were you supposed to decrement when you have the 4 loop? Because I think it says
Good.
plus plus I.
Yeah, that's it. That's it right there. Does everyone see that? See, we're starting at a big number here. We're making, I has to start at the end and then go down. This is the last index. So we need to go down. So we need to decrement rather than increment. Good job. I didn't even know that. So you caught it before me. All right, let's see if we pass the test code now. It works. So this was the hardest problem, this one here. But it's still not too bad. Any questions? Okay, that's it then.